So we're going to have a look at the topic in Unit 2 of AS Chemistry, and that's in the rates topic or kinetics topic. So the first part of that topic talks about collision theory, which is covered in your notes and is not much more of a challenge than collision theory at GCSE, so I'm not going to cover that here. I am going to talk about the second part of the kinetics, which is new at AS level, and that's to do with Maxwell Boltzmann distribution of molecular energies. So essentially this is really to do with what we call ideal gas, distribution of molecular energies in an ideal gas, but it can be applied to cover most reaction mixtures, so that's what we use it for at AS Chemistry. So what is it really? Well, first of all, it is the molecular distributions of the molecules or the particles within a reaction mixture. So if I was, for example, able to take a reaction mixture here of A and B, and I was able to plot the distribution of the energies or the speeds of all of these particles, and I would plot them along here with my little bars, like so. Okay, so it's some sort of magic microscope, okay, which allowed me to look at the speeds of all of these and then somehow map them. Okay, and I plot those against a number of particles with those particular energies or speeds. Okay, well obviously I'm showing here that these have discrete quantities of energy and discrete speeds in these particles. But that is not true within a substance here, and actually they have a continuum of speeds within the reaction mixture. So the red line is what you will see whenever you're talking about a Maxwell Boltzmann distribution of molecular energies. And therefore, all the particles in this mixture A and B are represented by these black bars, or in other words, by the area under this line or this curve. Okay? So this whole area represents the number of particles. This part here represents the number of particles which have the highest kinetic energy, okay, or highest speed. Okay, on average, you'll see this graph. It's slightly skewed if my artwork is correct, slightly skewed, okay, to having more particles on this side, or it should be, right? So the average or the mean kinetic energy of the particles will lie about there. Okay, so you've got the mean kinetic energy probably about there. Okay, so those are a couple of things that you might want to know. You'll also want to note that whenever you're asked to sketch this graph, you always start at the 0, 0 point. So you're essentially saying that no particles have no energy. So all particles have a certain amount of energy. So what we're going to look at is how does this graph change as we change the concentration, as we change the temperature, and as we introduce a catalyst into the equation. So first of all, how does the shape of the graph change, and how do we redraw that as A-level students in an exam? And secondly, how do we use that change in shape of the distribution curve to explain how a rate of a reaction actually increases or decreases? So we'll have a look at that now. Okay, so the first thing that we'll look at is if we take a Maxwell Boltzmann distribution graph, how do we change that to illustrate that the temperature of a particular reaction mixture has increased. Okay, so if we look at this graph here, again we'll see it's the same sort of graph, and if we look at T1, that's the temperature. Okay, and importantly here we've got the activation energy plotted on this one, which I didn't have at the start. And what we're showing here in T1, if we follow T1, we're showing this dark shaded area is the particles which have got the activation energy or greater, or in other words, can react. And if you're asked to plot an activation energy on this type of graph, please, I'll not give the reasons why, but please plot it well to the right hand side. Don't be plotting it here or here, you will not get the marks. So if I was to say to you what's the percentage of particles in T1 with the activation energy, hopefully you'd say, it looks to me off my eye about 15%. If I increase the temperature, then how does this graph change? This is the first thing we need to do. Well, obviously if I increase the temperature, I'm going to give the particles the same, or I'm going to give them more energy. But I'm not going to increase the number of particles. And if you remember earlier, we said the number of particles is represented by the area under the curve. So therefore the area under the curve of T1 should be, to the examiner's eye, roughly the same as the area under the curve for T2. And it is here, you can see that. But what happens in T2 is, and this is what you've got to show in your trace, is that the peak moves to the right a little bit, and not only does it move to the right a little bit, but obviously the peak moves down, and the whole graph in T2 here at the higher temperature, okay, you will now see has flattened out a little bit. How do we use this to explain why increasing the temperature increases the rate? Well, if you look now at the number of particles with the activation energy or greater, we have a much larger shaded area than we had just at T1, the lower temperature, which was the dark shaded area. So we now have, and this is important, we have a greater percentage, so it's maybe about 25% of the particles with the activation energy, okay, or greater, equal to or greater than the activation energy, and therefore we will get more successful collisions per second and a faster rate of reaction. So that's how we can use the Maxwell Boltzmann distribution of molecular energies to illustrate how temperature, okay, changes the rate of reaction. So you will have to plot new lines. The examiner may say at a higher temperature or a lower temperature. So please make sure and practice those. Remember to start at 0, 0 as well. Right, we're going to have a look then, okay, if we were to take a reaction mixture, and instead of changing the temperature this time, what we'll do is we are going to change the concentration. So if we said we have an aqueous solution and we change the concentration of that. So we'll have a look at this graph here. So if I change the concentration, the important thing is I'm not changing the temperature, so the overall distribution of energies within that reaction mixture will be exactly the same. But I'm going to have this time fewer particles if I reduce the concentration. So how do I show that? How do I show the same sort of distribution of energies, but I've got fewer particles? Well, I've just kind of got a mirror, so we start at 0, 0 again. I've got to mirror this curve. I'll do it as best I can. Okay. So if I call this concentration 1 and concentration 2, where concentration 2 is less than concentration 1. And now you'll see that we have the same distribution of energies, but we have fewer particles. And the most important thing then, okay, so that's how you would plot your graph, okay, and the most important thing then when you're explaining why reducing concentration reduces rate of reaction is we now have a smaller percentage, or a smaller number, sorry, not percentage, of the particles which have the activation energy. So if we look at before, okay, in the blue region here, with at C1 at the higher, we had the blue particles had the activation energy, whereas at C2 at the lower concentration, we just have the red. So we're going to have fewer successful collisions per second because we've got fewer molecules per cubic centimetre, and that will reduce the rate of reaction. Okay, the next thing I want to look at then is how do I change, or how does a catalyst, change the rate of reaction, and how do I show that on a Maxwell Boltzmann distribution? Well, what does a catalyst do? Well, it reduces the activation energy, it gives the reaction a different route, okay, and in doing so reduces the activation energy, and therefore we would plot, and I'll just plot EA there, activation energy, with the catalyst there. So that then, okay, shows me that at the start I had, let's say, what's that? It's maybe 20% of the particles had the activation energy without a catalyst. I introduce a catalyst, okay, lower the activation energy, so I move it to the left. This is the energy axis, and I now have these additional particles. So that's maybe up to 30% of the particles of the activation energy. So again, I'm going to have more successful collisions, and if I have more successful collisions, I'm going to have more successful collisions per second, and therefore a faster rate of a reaction. Okay, so that is how you would use the graph to first of all plot on it where the EA kata is, and then explain why that increases the rate of the reaction. Do not plot this line down in this region here, okay? Keep it up just slightly to the left of the one that's on the exam already, or on the paper. Don't get into this large region down here. Okay, we'll have a quick look at a couple of reaction profiles then, guys. Just sometimes students have a little bit of difficulty with reaction profiles, okay? So if we look at this one here, this one is one for an endothermic reaction. How do I know that? Well, I know that because this is my energy here, and this is my time here, my reaction profile. Okay, my reactants are of less energy than my products, so energy must have been taken in, okay, and therefore it must be an endothermic reaction. My activation energy is here, so it's right from the reactants to the peak of this energy barrier here. Okay, a lot of people will frequently draw the activation energy from there to there. That's wrong, okay. Looks a bit like that on the exothermic one, and I think people get a little bit confused. And then we have our delta H, okay, our enthalpy change, and that is the difference in energy between products, which would be there, sorry about the wobbly line, and reactants, which would be there. So that's that value there. If you were to take this and the examiner said, okay, well that's fine, but show me how this reaction profile changes with a catalyst. Remember, again, a catalyst reduces activation energy, so you would replot activation energy on it, but you would show it now as being reduced. So it was originally from there to there, now it's from there to there. Okay, do not bring your hump of your activation energy below that line that my pen is on now. And your delta H remains the same. Introducing a catalyst doesn't change the overall energy change, it just reduces the activation energy and speeds the reaction up. If we looked at the same, but this time for an exothermic reaction, okay, exothermic, we know it's exothermic because the products have less energy than the reactions, so in other words, energy must have been lost, so exothermic. This time activation energy is again from where the reactants start to the hump, the barrier, okay, here, and then delta H, okay, here, our enthalpy change is the difference in enthalpy or energy between reactants and products, so that is this arrow here from there to there. And then if we go to apply a catalyst, the activation energy of the catalyst again is reduced, so it's this dashed line here. Okay, so if I'll just try and plot it on there with that double-headed arrow, it's very small, but hopefully you can see it just there. That's the activation energy with a catalyst. So hopefully that clears up a lot of sort of Maxwell Boltzmann stuff, guys, and you're able to draw the graphs, and not only draw them but then use them to explain why it is that there's a change in rate of reaction, and also deal with energy level or enthalpy level diagrams or reaction profiles, whatever you want to call them.